All right, everybody. I want to welcome you to this month's installment of our From Research to Implementation webinar. We've got some exciting stuff today that's a little bit different than some of the things that we've done in the past, but some really fun new kind of technology that's out there that we're seeing gain some traction, if you will, some traction there. So today we're going to talk about longitudinal grooving of asphalt pavements. So as always, we have Nathan Moore. He'll be joining us here in a couple minutes. Nathan got both his bachelor's and his master's degree from Auburn University and spent time as a research engineer in the NCAT laboratory before becoming the assistant director for test track research. And then my friend Brian Schleppe, who helped me out when I was in West Virginia a few times on some great things there. Brian spent a great career with the state of Ohio, looking at friction, looking at pavement characteristics and pavement measurements. And now Brian has got himself his own consulting firm. Again, looking at all the pavement characteristics and so forth. So with that, I want to introduce the longitudinal grooving of asphalt pavements. And some of the work that has been done there. As always, please keep yourself muted and put any questions that you have in the chat box. We're going to flip things around a little bit today, and we're going to ask our industry perspective guest to go first. So, Brian, would you like to go ahead and start sharing, please?
All right. Well, good morning, and thank you for the opportunity to let me speak on this topic. And as as Travis said, I spent 35 years with the Ohio DOT, and probably 25 years of that was centered around some form or fashion in the friction management area. And I actually developed a friction management program and tried to implement it before I retired in 21. This is sort of what I'm going to try to cover today. I would like to say that I was with the DOT, ODOT, for 35 years, retired end of July 21. So I'm not representing ODOT, but I might say things like we and us and that sort of thing. Just keep in mind, I'm not representing ODOT. I'm just sort of talking about my experiences and my time that was there. I'm not going to go into a whole lot of detail when it comes to case study locations or friction response data, just because of the sensitive nature of it. So, but I think you'll get the gist of what's going on, and I'll try to answer questions as best I can. So we'll talk a little bit about science and theory of tire pavement friction. It's going to be very abbreviated. I could probably spend a couple hours on that. No, nobody wants to do that today. So we'll just go through the quick and dirty to try to get you enough to understand what's going on and why things are important. We'll talk about what longitudinal diamond grooving is, how it improves tire pavement friction, particularly on asphalt surfaces. Again, we'll go over some case studies. And then I'll kind of talk about when and when not to consider using it to improve friction on an asphalt surface and some of the advantages of it. And so we'll go from there. So I always like to start out with this. I don't know the level of intelligence of the guy that came up with it, but I certainly believe this. When it comes to the pavement side, as long as you don't have obstructions to drainage, then tire pavement friction from the pavement side is exclusively a function of the micro texture and the macro texture. So what is micro and macro texture? These are a couple diagrams. I would want to highlight the source, Hartwig Kummer. This came out of 1966 Engineering Research Bulletin 94 from Penn State University, Unified Theory of Rubber and Tire Friction. It is a gold mine for understanding friction, even though it's old. And if you can't find a copy of it, I've got a scanned PDF of it. Just email me and let me know, and I'll get it in your hands. In any case, what's microtexture? Microtexture is the texture or roughness on the aggregate particles at that level, right? You maybe can't see it so well. And then macro texture is sort of the voids between your aggregate particles in the asphalt surface, right? And there's a couple mechanisms hear adhesion and hysteresis, and I think really everything's about hysteresis, and we'll talk about that just a little bit. And I don't want you to be, I guess I am going to have you sort of drinking from the fire hose here since we don't have a ton of time. So we'll try to cover the important stuff. So microtexture, as I kind of already mentioned, it's a lot easier to feel than it is to see because it's on the smaller end, right? So if you think about a tabletop or a glass surface, you rub your hand over it, you're not going to feel much friction or texture there. As opposed to, say, a 400 grit sandpaper, you can't really see a lot of texture, but when you run your fingers across it, you notice a big difference. So again, microtexture comes from the surface of the aggregates and their crystallinity. Some of your aggregates are going to maintain their microtexture longer because they're harder, and others are going to not maintain it as long because they're softer and will tend to polish over time. And one of the important features of microtexture, particularly when it is wet, is that it breaks through the uh, viscous water film on the surface so that you're not viscously hydroplaning. And we'll talk about that just a little bit. And again, you get friction from hysteresis, and I'll go into hysteresis a little bit more in a bit here, but hysteresis from the tire blocks themselves, sort of at a really small level, lower level of the spectrum. Microtexture, you need everywhere. Every part of your system, you need microtexture, whether it's high speed or low speed. It's actually gripping the road. So macrotexture, again, it's a lot easier to see. You still feel it as well, but it's easy to see. It's the spaces or voids between the aggregate particles on an asphalt surface, particularly a hot mix asphalt where you're rolling it for density. You're going to have a flat surface, and your macrotexture is all going to be negative, and it's going to be those air voids between the aggregate particles. Macrotexture does a couple things. It deters dynamic hydroplaning. It works with the tread pattern of a tire to form void channels or drainage channels to evacuate water when the surface is wet. And it also, the texture in that surface is going to deform the tire patch that meets contact with the tire with the surface. It's going to sort of make that tire float over it. And it's going to give you some friction from hysteresis or that rubber deformation. So the greater your speeds of your facility, the more macrotexture you really need to deter hydroplaning. And let me talk a little bit more about hysteresis in general. So if you take a paper clip and you start bending it back and forth really quick, it's going to heat up. And it's when you change the shape of that paper clip, that movement in there creates internal friction and heat. Same thing with the tire, right? Anytime you deform that rubber, change its shape, it's going to generate some heat. So when you're braking or trying to control your vehicle, that rubber deformation takes energy out of the system, and we call that hysteresis. So it's at a small level with the tread blocks, it's with the entire tire patch. And then for rolling resistance, it's actually the sidewalls bending from where the tire goes round to flat when it meets the surface, and then rebounding, and the edges of the tire sidewall squishing out. That's why your tires, if they're cold, maybe you drive to work. If you touch your tire after you get to work, you're going to notice it's not ambient temperature anymore. It's a lot warmer, and that's where a big part of rolling resistance comes from. So hysteresis is just changing the shape of the rubber, and it's taking energy out of the system. That's the main thing to remember. All right. So there's this three zones of the tire patch. Zone one, in a wet situation, right? The leading edge of your tire, zone one, is going to be dynamically hydroplaning until it pushes all that surface or bulk water out of the way. Once it pushes that bulk water out of the way, you're in zone two. You have this viscous film, and that's where your microtexture needs to break through that viscous film in order to make contact with the tire. When it does, you're in zone three, and that's what I would kind of call saturated surface wet, but that's really where they call it the dry contact region, where the rubber is physically making full contact with the road. Now, these zones can be bigger or larger depending on how fast you're going, how much water is on the road, the load on the tires, those sorts of things. If you could have everything could be completely zone one, and you're hydroplaning, you're sliding off the road, you have no control of your vehicle, or even zone one and two. If it's dry, everything you have is zone three. So just kind of keep those things in mind. And we primarily think about friction in wet conditions. It's also possible to have a friction issue when the road is dry, but I've never found a situation where we have a dry friction problem where we don't also have a wet friction problem. Anyway, let's move on here. So I thought I'd throw these two slides in if you are or are not familiar. We evaluated our friction in Ohio while I was there, and ODOT still does, to the best of my knowledge, since I've left, with the lock wheel skid testing unit, ASTM E274. There's two test tires. This is the rib tire, and I've got a blow up there worth a nickel into the depth of the tread pattern, but this tire is a lot more sensitive to micro texture, right? Because the ribs, or those voids in that tread pattern, are going to help evacuate the 0.5 millimeter water film that we put down when we drop a skid test. So this tire is a lot more sensitive to micro texture as opposed to the smooth tire, which depends on the surface of the pavement to evacuate the water. So it's really sensitive to both micro and macro texture. So when you use both of those and you look at the response data, you get a better idea of what's my problem. Is it micro or is it macro? Now, let's get into longitudinal diamond grooving. What I'm showing on the screen here, the upper picture is diamond ground asphalt surface, and it was taken right after grinding, after it dried off, before it was open to traffic. That's why you're seeing a few crumbs there in the grooves, but very tight saw blade spacing, right? The bottom picture is not quite as close up, but more to the right side of it, you can get an idea of what the grooves look like. They basically, these machines have an arbor. They have a bunch of diamond impregnated saw blades that with spacers in between them. So when you're grinding, you have very narrow spacing. When you're grooving, at least the spec in Ohio was to have them at 3/4 inches on center, which is what you're seeing in the picture. The big point that I want to make about grinding or grooving, or when you're using these diamond blades, it's an abrasive action. It's not an impact action. We're not hammering the material away. We're abrading it. We're actually cutting it. And when it comes to asphalt surfaces, even though it's a wet operation, you're generating heat. And what happens is you tend to heat up that bituminous material, and it sort of reseals the surface after it's cut. So we typically never see any long-term durability issues with grinding or grooving that we may from, say, carbide milling, if you will. One last thing I would say, if you're going to diamond groove an asphalt surface, if you have a longitudinal grooving spec for concrete bridge decks, use the same spec. Because if you want to go to a different groove spacing than what you're using in your state, it's going to cost you a lot more money, because they're going to have to remove that arbor and stack those blades with different spaces, and you'll just end up spending a lot more money that you probably don't need to spend. Anyway, so what's it do? It creates an abundance of macro texture, or at least sufficient, right? Because we're cutting grooves below the surface, and we're doing that without really having too much negative impact to the contact surface that the tire meets. We're cutting these really narrow slots into the pavement. They can be deep. The deeper we go, the more macro texture we can add. Again, it's all negative. Essentially no impact to your microtexture. And it also gives you a significant, what we would call a mechanical bite component. When I showed the slide earlier and we talked about Hartwig Kummer and that engineering research bulletin from 1966, he came up with the term mechanical interlock. But when you have these grooves and you have a tread block that falls into that groove, it takes a lot more energy to snap that thing out of that groove. So if you longitudinally groove, particularly through a horizontal curve, it's going to tend to keep your vehicle not only on the road, but in your lane. So if you have to hit the brakes when it's wet in a curve, you're going to tend to more stay in your lane, not go off the road and hit the barrier, or have another car slide off the road and enter your lane. So it kind of holds you in the lane and it certainly increases the hysteretic function of what's going on. So 2013, urban interstate in Ohio, every time it rained, we were having an abundance of wet crashes, particularly truck crashes. And I think what was happening, uh, the almost all of the wet truck crashes were reported because the trucks were crashing into the guardrail or into the median barrier, which was concrete, and they weren't able to drive away. Where many times where a car loses control, if they do bump the guardrail or the median barrier, if they can drive away, they might do so, particularly if they're not in the greatest insurance situation. But every truck had no choice; they were crashing, and it turned out the we were ODOT was not responsible for. We had an agreement with the city, so they had to take care of the damage to the barrier wall, which was probably delayed the fix on this thing a little bit. Since we weren't directly responsible for it, sort of the feedback loop took a little longer to correct. But in any case, every time it was wet, we had a problem. An abundance of truck crashes. There's vertical curves, there's horizontal curves, supers, and it was a problem. And this was shortly, I would say, 1 to 2 years. It might have been sooner after resurfacing. We skid tested it. We had pretty decent rib tire numbers. We might have liked to have those a smidge higher, which kind of indicated that our microtexture was pretty good. We tested with the smooth tire, and we really had some poor smooth tire numbers, which told us, okay, once we get the water away, we have pretty good friction, but we're not doing enough to get the water away. We need more macro texture. We did some research about the only place that we could find where asphalt surfaces were being grooved, either longitudinally or transversely, were at airports and some of your lower volume airports. We're not talking commercial airports so much. But how comparable was that, right? So we had a problem. So here's another photo. You can see some of the curves, some of the vertical curve coming into a horizontal. I'd like to also point out the slippery when wet sign. We see those very frequently. If somebody's putting that kind of sign up, it might be an indication you have a problem, right? And maybe the sign isn't the only treatment we ought to be using. Anyway, these photos are from about 2017, I believe, and the treatment was done in 2013, and I think this thing was resurfaced in probably 11 or 12. But it's a high stress location, lot of truck traffic. And this is just kind of looking out the rear view. So what were our treatment options? We're really looking at, gosh, do we put a high friction surface treatment on this thing? That's going to be extremely expensive, take a lot of time to sell, and we definitely need decent weather, warm weather to execute it. We could cover it up with some other kind of surface course. Again, that was going to take a lot of time, and there was a big process to go through and expensive to do. And I had suggested, I said, hey, why don't we try longitudinally diamond grooving it like we would a bridge deck? We can get out there, we can do it fast. We got to help get rid of the water, give us a little more mechanical bite. And so we started talking about it. And the area engineer out there was concerned that if we did it like a bridge deck, he was worried about the edges at the saw cuts raveling. And he was also concerned that the lands and the curves were going to slide or shove. So we tried it. And what we found out was there was really no evidence of accelerated deterioration. We didn't see the lands sliding over. They held up really well. But we didn't completely eliminate our wet truck crashes, but we greatly reduced them. I mean, they were really pleased with the results that they found from this treatment. So it wasn't a perfect fix, but it did a lot of good. What we found out later was through the super, there was an area where we needed an additional 18 inches of elevation tapering down to zero on the other side to restore the proper cross slope and super. So what that meant was when it rained, we had a lot of water flowing along the lane as opposed to across. So the lanes were carrying more water than they should have. So that extra macro texture from the grooves helped to evacuate more of that water. Once they discovered that geometry issue, they sold a project, they fixed the geometry. So that section was covered up and had probably a better long-term fix. But that was the first place we tried it, 2013. Now, this is another location on an interstate in another urban area. This stretch of the interstate had a design exception because you can see those signs, 35-mile-an-hour curve. We've got 4 lanes going through that curve. We had an abundance of wet crashes after the resurfacing. And again, these pictures, I went back through our old photo log that's available, and I didn't have pictures of the treatment immediately following the grooving. But in any case, they started having the wet crashes soon after the resurfacing. Now, this curve, let me back up. This curve was too tight. I don't know if you can see it. We could not groove this direction. The curve was too tight, and the blades would have bound up from the turning of the machine. So just was not an option. So in this direction, we ended up, the district decided to sell a contract in this direction to micro mill it. And then the opposite direction, the curve wasn't as tight. And this is the direction that we diamond grooved. And just mostly a horizontal curve. You can see they've got flashing chevrons through there. And we had really good rib tire numbers, which told us our microtexture was good. And when that was resurfaced, they used Ontario trap rock that was imported out of Ontario over across the lake. Though that's a polish resistant aggregate, so your microtexture holds up pretty well for a long time. We grew this thing, and it solved the problem. We didn't continue to have any more higher than expected level of wet crashes, so it worked really, really well. The problem, the other side, they micro milled it, which kind of gives you both positive and negative texture. It ends up increasing the load on the aggregate particles because you're reducing the contact area, and it sort of accelerates the polishing. So even though we had trap rock, it started to polish, and almost immediately, it wasn't like super fast, but both the ribbed and the smooth tire numbers in the opposite direction were micro milled began to drop. But this direction that we longitudinally grooved maintained its friction for quite a while. So the only problem, the district was concerned with the opposite direction. They had another resurfacing project that just the area of this curve, they tied this into it and resurfaced both directions. So we didn't get a long-term test out of this one, but this worked very effectively through this curve for the period of time that was out there, and we didn't see any deterioration. So this is an expressway, a divided 4-lane urban expressway outside one of our bigger cities. Wet crashes, again, right after resurfacing. We tested it. We had really good to great rib tire numbers, and then we had really pretty poor smooth tire numbers, which again was an indication that surface did not have enough macro texture. And you can see the horizontal curve here. There's another direction. I think you can see in the picture the machine had a 3 or 4 foot wide head, so they could make 3 passes across the lane. And of course, we did not groove over the striping, so that's why you see the discoloration there. And post-treatment, it solved the wet crash problem. Essentially, no change at all in our rib tire numbers, which were already good. Smooth tire numbers doubled, and they maintained. This section has performed exceedingly well through its entire service life. It might have been resurfaced last year or slated for resurfacing this year. So we're talking 10, 12 plus years that this treatment has worked and worked reliably. No signs of accelerated distress or deterioration compared to the non-grooved sections that were paved at the same time with the same material. All right, so here's another one. This is a 2-lane road. Again, right after resurfacing, it starts raining, we have wet crashes. The surface was a fine graded polymer hot mix overlay. In Ohio, we would call that a smooth seal type B. They go down 3/4 to an inch thick, a whole lot of binder, Probably PG 70 or a 7622 was used. So really strong binder. These smooth seals have a bunch of natural sand in them, so they have a really high silicon dioxide content, which gives them great microtexture. But they're so they have such a small grading of aggregate, right? It's sand and stuff slightly larger than sand. Out the gate, they just don't have the ability to have an abundance of macrotexture. So just in the high stress locations, the curves on this project, we had wet crashes, and I'll show you a couple other pictures uh, where we did the grooving. It was probably, I don't know, half mile, maybe less than a half mile, that both lanes that we grooved. This guardrail was getting damaged by cars going both directions. I'll show you the same guardrail from the opposite direction. So you can see we began grooving right at the guardrail. They were hitting a little bit farther upstream. So we grooved this. There was a lot of concern, particularly with our asphalt materials engineer. Was afraid that given the thin lift of the surface, that if we grooved it, we were going to see accelerated deterioration, that we might see accelerated cracking. And I said, look, what else are we going to do? We're having serious injuries. We're damaging our barrier. Our maintenance folks are going out there all the time. We got to do something. We've got to do something quick. So he agreed. It maybe wasn't his best from a durability perspective. He wasn't sure, but from a safety perspective, we had to do something and do something quick. It has worked. This was done probably 2021. It's still performing well today. We see no signs of accelerated deterioration. And I mean, the smooth seals are a stable mix, particularly with the binder that they're using. So lessons learned, or what some suggestions. When would I consider using longitudinal diamond grooving to improve your friction on your AC surfaces? Well, obviously you have to have evidence of wet crashes. It could be from law enforcement, ITS, crash reports. Uh, if you're waiting for crash reports, a lot of times the safety folks like to watch a 3-year trend of crashes before and after a treatment. That's probably too late. You want to look at damage that's going on. When you see an uptick, or you think you're aware of wet crashes from barrier sign repair and replacement, that's a good idea that you got wet crashes, right? So your surface needs to be in good condition and structurally sound. So we don't I wouldn't suggest using it on a soft mix. If you've got bleeding, flushing, kneading, what I call plastic flow rutting. It's not really structural, right? It's this surface court might be pushing or shoving and giving us the rutting. So that would be a bad candidate. You also want microtexture that's at least fair to good at a minimum. Or I wouldn't suggest doing it if your microtexture is poor. And if your root cause of your problem is a lack of macrotexture, it's a good candidate. One of the problems we often see is our maintenance of traffic policies kind of are at odds with letting the mat cool down, right? So we could have a mix that should give us good friction from both a micro and macro texture perspective. But if we open that thing up to traffic before that mat gets cool, a lot of times we can roll that macro texture right out of it. So I thought that was important to throw in there. Um, uh, any case, when not to consider using it, probably wouldn't do it on an older surface. And most of the time, at least in our experience, we would do a lot of wet crash investigations. We weren't doing network testing. So when a problem cropped up, it was usually soon after resurfacing, and that's when we would evaluate them, right? But older surfaces, if they're raveled, rutted, cracked, poor condition, bleeding, you're probably not going to try it. If microtexture or polishing is the root cause of your problem, grooving's probably not going to help you a whole lot. Again, you don't want to do it on a soft mix. If your road's rutted, they're going to go in there to groove. They're going to groove the heck out of the sides, but they're not going to reach into the wheel track. So that's another problem. Again, insufficient. If your root problem is insufficient, sorry, that's a typo. It should be insufficient macrotexture. Sorry. And you really don't want to try it in tight horizontal curves, because the machine's gonna bind up and heat up, and they'll ruin the blades. And so you have to look at the curvature of the site that you're considering. And finally, what are the advantages of using longitudinal diamond grinding, or grooving rather? It's easy and quick. If you have a problem, if you've got a fatality or serious injuries out there, that really ramps up the pressure to do something. It's relatively easy, it's relatively quick to execute, and it's inexpensive. And you're going to have contractors in your state that are probably grooving bridge decks, so you should have the equipment there to do the job. It increases your macro texture with basically no loss of microtexture, or without any downside there. And it's leaving that surface flat, right? So it's leaving the tire contact patch with an even distribution. So we haven't seen really any evidence of any accelerated polishing where we've done this. Again, you get the mechanical bite, which holds people in the lanes. It's great for curves. And probably the biggest thing that we found for the locations that have been out there, we've got evidence on a couple anyway that this is a really durable and has great longevity. It will, in a lot of cases, I'm confident it'll last through the end of the service life. So it's not a magic bullet for everything. It's like tools in the toolbox, right? You don't use a hammer when you need a saw. But under certain circumstances, this is a really good fix to solve some friction problems on some of your friction problems on your asphalt surfaces. So there we go. I guess I'll pitch it over to, I don't know how you want to handle questions. Just
I'll,
pitch it over to maybe to Nathan, and then
yeah, I'll go
questions.
ahead and Brian, I'll go ahead and I'll touch the NCAT side, and then we'll team up on questions. But I do want to reiterate, actually, I just saw somebody went ahead and put a question in the chat. Go ahead and get your questions in there. If it's something quick and easy, Travis can answer it, but otherwise we'll have that as you can tee us up for the end. I do want to take a brief 30 seconds of personal privilege. I am thrilled to get to share this webinar with Brian. Brian has probably forgotten more about this kind of stuff than I will ever know. And much of what I have learned, I've actually learned from Brian. And so I think it makes perfect sense for us to deviate a little bit and let him go first, especially because ODOT has been doing this now for a decade. I think Brian, you said the first one was 2013. So I'm really happy to share the stage, or whatever you want to say, with Brian. He's a great resource for me personally. So with that, let's talk about North Carolina's longitudinal grooving experiment on the NCAT test track. I see Andrew Wargo, our friend from North Carolina, is on here. So he has been also very instrumental in pushing this forward. So I don't have to talk a ton about grooving. I think Brian did a wonderful job hitting the highlights and really getting into the details. It's one of those things where, as is the case with any tool in life, you really need to know when it works and when it doesn't work. So North Carolina DOT came to us and they say, look, we are investigating early pavement life macro texture. We don't have a microtexture problem. North Carolina is blessed with really good aggregates, granite aggregates across the majority of the state. So polish resistance is not a problem. But in some of the overlays, they were saying, like, we want to figure out, like, is it possible to increase macro texture on some of these routes? And they were also considering some other stuff like shot blasting, which they have some experience in their state. And also mix design changes. So they came to us and they said, look, we've already kind of got some field sections out on shot blasting, but we want to know, can you improve texture, macro texture specifically, through mix design changes, so like through the gradation, and also longitudinal grooving. So we're going to focus on the grooving today. So we did this in October of 2024. We had finished paving the test track, but we had not opened up traffic yet. And so Southeast Grinded and Grooving, they're a grinding and grooving contractor out of Georgia, came, and they were actually gracious enough to donate this service. They were really excited about having the opportunity. I like this picture because you can kind of see, if you're familiar with the track, this is in section W4. W4 is sort of at the maximum super elevation. And that track is banked at about 15%. That's going to come in important later. If the grooves can withstand the lateral forces from our trucks trying to kick out, and the lateral shear forces on the track, there's really not other. Brian talked a lot about like high intensity areas or high stress areas. This is very much a high stress area, and so that is a great place to try something like this. So I thought Brian's point about standard longitudinal grooving specs was great, and we actually got the same advice. And shout out to Larry Schofield with the Grinding and Grooving Association. He said, "Keep it simple, don't change anything." And so that's what we did. We kept it simple. Section W4, just to get, and it's just some information on the mix itself. It was placed in 2021, also funded by the North Carolina DOT. It had 40% recycled binder in it. There was 25% wrap and 5% RAS, that's shingles. And so it was stiff. It did have a base 58-28 binder in it, but it was a high recycled binder section. So the original point of this test section was to investigate bond strength, but it ended up being a pretty good place to try grooving of what could be considered a more brittle mix, or this was a really fine graded mix, or especially something with high recycled content. So I'll show you a couple pictures now from whenever we were out there. And again, you can see the North Carolina granite popping up in this picture. I think this is a really nice picture, actually, where you can see the microtexture and the aggregates, and it's also a worn-in section. For being a fine-graded mix, this actually had pretty high macro texture and smooth tire numbers prior to grooving. So if this was in the field, it might not be the best application, or it might not be a necessity because it was already doing fine, but it offered a good opportunity for us to look at in a really high stress environment with a mix that is tending towards brittle, what kind of performance can we see? So even though it didn't necessarily need it, it was still a good candidate for grooving. After placement, I went out there to, this was, I think, in January, and during a rain event, and I got just really curious. I wanted to know how the spray looked and how the surface texture looked. So I went out there in the rain after we placed it, and I'm showing you here, this is a brand new overlay. So these sections are actually adjacent to one another. So get a sense for the film of water on this section compared to the groove section. And you can see very clearly you've got a lot more islands of aggregate microtexture popping up. The film of water is significantly reduced in this picture. So you can imagine, as you are doing some type of rapid acceleration or deceleration or turning or braking on a surface like this, your tire is going to touch rocks a lot faster on a surface like this than a surface like this. And that's why this is such a good tool to improve macro texture on certain routes. I'm going to show you sort of a panoramic view. So we have in our pathway vehicle, our survey conditioning van, we have a GoPro where we take panoramic images of the test track. And so I'm going to just sort of slowly drag this across the screen. And I want to point out, you can see some surface deformities in that beginning. That's the transition. We don't put a lot of stock into that. That's where you've got transitions between mixes and it's a little weak. But you can see that as you progress through the test section, there's not a lot of performance issues. And those cores that you see there, those are from the previous study. What I want to point out is, even though it's a high intensity area, there's some of the grooves that have, that occasionally they fill up with a little bit of rubber that the trucks don't clean out, and the water will come through. But in general, we're very happy with the grooving performance that we've seen, and not just in terms of visually, but also the data that I'm about to show you. But we are very pleased with the quality of the surface, and given this, the type of traffic that we are putting on this test section is it's accelerated and extremely heavy. So the shear forces are constant and brutal. And so every single time these grooves are being stressed, and it's the rubber in the tire is deforming. And I thought Brian's explanation of hysteresis was really powerful. If you've never touched your tire after you've driven for a little while, you haven't lived. So I would recommend that to anyone. So anyway, it's a great opportunity to evaluate grooving. One of the questions, though, that we had was, over time, are these things going to wear out? So I'm showing you average groove depths with traffic. And we've got, so this is your typical range. It's 3/16 of an inch, plus or minus a 1/16 of an inch. So we started doing this around after about 1 million easels, and our initial average was actually, it was somewhere a little bit north of 3/16 of an inch. I swapped it over to millimeters here because it was a little easier to graph. But that range, that orange bar, is your typical groove depth range. And so we're going to monitor this over time and just see, how do these things last, and when do they sort of drop down to under 1/8 of an inch? Because that gives us an indicator of, in a super elevated section like this, in a curve, how much traffic can you expect this thing to stand up to? And so we expect it to continue to maybe even flatten out a little bit. So we'll keep you updated on this. But so far we're where we want to be, and there is a very slow decline. And this is an average over 3 different locations. So some of them are actually a little higher than this. Some of them are a little bit lower, but that's a pretty good snapshot of where we stand. Macro texture performance. This is sort of getting into some of that stuff that Brian was talking about. Notice first the orange section, the W4B no grooved section. So we took that W4 and we only grooved half of it. We grooved the first half, the first 100 feet, and we left the other half. Now, something to point out, the orange line, the W4B, this is actually a really high macro texture surface. Not one that you would typically expect from a fine graded 9.5 mix. So the delta between a control and then a grooved is typically going to be even larger than it is here. But even here, a 0.2 millimeter increase in macro texture is significant, and you'll see it in the data later. But normally when you're doing this, you have a serious macro texture problem, and you're nowhere close to 0.8 millimeter of mean profile depth. You're way below this, and you could still expect dramatic increases to over 1 millimeter in mean profile depth. So yeah, that's kind of what I talked about here is, W4B is abnormally high. So I don't want people to think that you're only going to get an increase of about 0.2. You can expect significant bumps in macro texture, and grooving should take you, up above 1 ballpark. So let's talk about ribbed and smooth tire numbers. I thought, Brian, again, I couldn't have said it better, and I think your pictures are better than mine. You did a great job of talking about the differences in ribbed tire and smooth tire, and so I want to corroborate what he's saying. We're finding the exact same things. When you use a ribbed tire, and that I've got the photo there on the left, you've got channels for the water to go. So as this tire is locking up and dragging across the surface of the road, the water is getting sucked up into the grooves, and you have dry friction underneath the tire and in that contact patch. That's how the treads in our own tires work. If you have brand new tires, it's going to perform somewhat like this, where you have plenty of tread depth and plenty of channels and opportunity for the water to come up into the tires, get off the surface, and then get out from under the tire. Because even a film of water about the depth of a hair can reduce friction 30-something%. I think there's an AASHTO report on driving down lane departures that has a statistic like that. I think I've quoted that correctly. So even a hair of film thickness, water thickness of on the surface. If you don't remove it, it's going to significantly reduce your friction. So that's why we need our pavements to be able to do that. But that's really what the tires, that's their primary job, is to get rid of the water. And so with that being said, you really don't need macro texture in order to get higher rib tire numbers. And you can see that here. You've got your groove section. I don't know if you can see my mouse. I'll put on my laser pointer. You've got the groove section here, which is just marginally better than the no groove section. I think I've seen some data before that sometimes grooving can increase your rib tire numbers maybe 10%. And so we've seen that here, whereas your grooving can improve smooth tire numbers by double or 75%. And I'll show you some stuff in a second. But this very much agrees with what Brian said, that if you have a polish resistant aggregate problem, and if you have low rib tire numbers, odds are grooving is not the appropriate solution. But if you do have good rib tire numbers and you've got really good polish resistant aggregates, granites, trap rocks, sandstones, gravels, things like that, with a high silica or quartz, you're not going to have an aggregate polishing problem, but you may have a low macro texture, and grooving is right. And so let's talk about smooth tire numbers. So in our data, we did smooth tire testing before and after grooving, and we saw 35% improvement. And Brian's probably sitting over there saying like, that's all only 35%. Keep in mind, we already had pretty high pre-grooving numbers for a fine graded, dense graded asphalt mix. It had already kind of raveled off a little bit, and so you had lots of those fine particles like your 8s and your popping up and giving you the macro texture you need. Very similar to what Brian was describing when he was talking about I think you call them the smooth seals in Ohio. But nonetheless, even grooving here, we saw a 35% improvement. And so now here's a picture of a smooth tire where you can actually see a pronounced difference between the two. Not as high as some of the stuff that Brian was showing, where you've got double the numbers. But again, remember, we were already doing pretty well, and this mix was not necessarily a candidate for grooving because of its poor performance. It was a candidate for grooving because of the environment it was placed in terms of high shear stress, high lateral shear stress, in a curves, and accelerated traffic. How do the grooves stand up in a place like that? You would expect to see, if we had a poor macro texture problem, your orange line would be significantly reduced, and you would see a huge doubling, for example, like Brian reported. But we're very happy with what we're seeing so far, and this kind of tracks with our expectations. So to kind of close out and get to some questions, in summary, longitudinal grooving significantly improved macro texture, and it's a really good friction countermeasure, especially for wet friction improvement. Or another way of thinking about that is if you have low macro texture, a lot of times those things are going to go hand in hand. And you can see the data clearly, both in terms of a measured a measured property of the pavement, the mean profile depth, but also the response from the smooth tire. It's very much telling you that we're getting what we had thought. We are getting clear indicators of improved macro texture, and that water is able to channel and get out from under the smooth tire. And this is a great treatment. And so what we found is that even in a 3-year-old asphalt, which had some high recycled content, it has been durable. It is seeing some signs of wear, but nothing to the point where we would say that the performance is degrading. We're pretty happy with where we stand. So that's all I've got for me. I do want to just briefly summarize some recommendations before we get into some questions. First of all, I think Brian and I both touched on this. Grooving is a great tool. It's an excellent tool to reduce wet crashes and reduce hydroplaning potential and improve wet friction numbers. That's exactly what it's designed to do. It's really nice when you can take something that is off the shelf. I talk about this a lot when I talk about grooving. Listen, this is a technology that is it's already vetted. It's been used on thousands of lane miles. It's on all the airports. This is a technology that works, and there's already specifications that are written for it, and there's already contractors and industry out there. So this is an off the shelf solution. So that should give comfort to safety engineers or DOT decision makers who are sitting there having to decide, what do we do if your problem sort of matches up with some of the criteria that Brian showed. This is off the shelf, ready to go. And it helps that you can just keep the same grooving specs and nobody's got to change out diamond or saw cutting or diamond grooving patterns. You do want to use it as a targeted solution. We're not saying that you need to do this on all your asphalts. Absolutely not. Budgets can't handle that, nor is it necessary. But you could use it as a target solution in high stress areas. Be careful about geometry. There are some curves that are just too tight that you're probably not going to be able to do this appropriately. You will find that effects of grooving are going to be muted on the rib tire test results, but that's okay. That's not a bad thing. It should be expected, but you don't want to use it. If you have low rib tire numbers, it's probably because you've got polish resistant aggregate problems or polish susceptible aggregate problems, not necessarily, maybe a couple other things going on, but it may not be a good target, a good tool for that. And it's not going to solve problems of having polish resistant aggregate. All you're really going to do is just get the water off, and you're still depending on the aggregates to bite the tires and to provide that hysteresis. So with that, here's our contact information. So I've got Brian's email there. Second, again, he's a wizard. He's a wealth of knowledge, and I would recommend anybody to chat with him on this. But we've got time for questions.
But I think one of the things that that has come up a bunch of times in here, and I think you guys covered really well, is that it's the same equipment. It's the same equipment that has been being used on all sorts of other surfaces. There were quite a few questions about like the aggregates that maybe are in Ohio. Brian, would you speak to that for a moment?
Yeah, right. So I kind of what I said in the text box was, Ohio is blessed with a lot of limestones and dolomites. That's probably, we probably have more of that as a local aggregate source than, we do have some gravels and whatnot. We don't have an abundance of polish resistant materials. So for the one location that I mentioned, the Ontario trap rock, that was imported across the lake to make that, I guess, economically feasible, imported material. So you have to build roads with what you have. So, I think ODOT is still sort of looking at what can we blend, to get better microtexture performance and those sorts of things. But there's some other situations where, we've got a district that doesn't have an interstate that runs through it and only a couple of divided highways. The majority of the roads there, 2 lanes and probably, 55-mile-an-hour speed limits, but hilly and curvy. The same materials that we used to build those roads, 2 decades ago, where they lasted their entire service life, aren't now because the truck volumes have increased. So we're seeing things polishing before they get to the end of their life and being a friction problem. That's one example of some of the things that, we have to try to, deal with, not necessarily where longitudinal diamond grooving would help you, but the materials are a big part of the challenge for sure.
Travis, I'm going to jump ahead and steal one. Greg Scholler, you have a great question. Asking about direct comparison between OGFC and grooving. I had the same question, so that's why I ran out there when in the rain one time, and I actually have some videos that I'd be willing to show you if I'd have to find them, where I was curious about truck spray or water spray. And what I found, and this was also confirmed by Larry Schofield, was really once those grooves fill up with water, you have just the same amount of truck spray as you would on a typical route. You may have early on in the rain event, until you saturate the grooves, you may have reduced truck spray, but that water's not really, going off the side necessarily immediately. It's still there in the grooves. And so the truck spray is really no different between the two. But from a macro texture perspective, they are very similar. And so you could expect some smooth tire numbers to be similar. So one of the benefits of OGFC is something that's hard to quantify is water spray, and so there's a safety element that you can't really get that from a friction test, but OGFC is definitely better than grooving when it comes to that. But when it comes to macro texture, they are very similar. So I also saw Todd Mansell had a question about after diamond grinding, their design criteria to follow with respect to groove spacing, center to center. It's all fairly new to me. And then it turns out I was answering the question as Todd wrote that. Yeah, so that's all. Most states kind of already have that those specifications for concrete, and just sort of copy and paste. It's as off the shelf as they come, and that's one of the reasons I really like it.
Nathan, Todd was also asking about what it does to the surface. Does it greatly reduce the surface area? It is going to reduce the area that you have with the tire contact patch because you have less surface. We have not seen, everywhere that I was a part of doing skid testing with both smooth and rib tire, where we did before and after testing, where we longitudinally diamond grooved, we really did not see a significant change in our rib tire numbers. And I think there's two reasons for that. Even though you are decreasing the surface contact area, you are evacuating more water than that rib tire can evacuate on its own. So you get a little more contact even because you're getting more of that water away. The other thing is we don't see those surfaces polished, even though the load vehicle to vehicle, tire to tire is increased because the surface area has gotten smaller. But when you're grooving that surface, particularly hot mix asphalt surface, that surface is completely flat. So the load's evenly distributed on the surface. So I think that's why we're not seeing an increased polish where we're doing the grooving. And then you do get the added benefit of those tread blocks. The tread blocks comply, and they kind of force themselves into those grooves. And particularly at the edges, you get more friction from that, what I'm calling mechanical bite or mechanical interlock. So to me, it's kind of a beautiful thing because you're increasing your macro texture. If you want more, you just go deeper, and then you're not sacrificing your width. Now there's a limit to how far you can go, but hopefully I addressed your question there.
So I'll sort of summarize a couple more of these. Tim Ashenbrenner had a question about protocols, the decision trees, and things like that. And Brian is probably the foremost expert and resource on something like that. I will say there's a NCHRP project coming up where it's all about optimized friction treatment strategies, where if this is your problem, what are the options that you have, and it's very much like a decision tree. And the two of us are actually on the panel for that. So I think Brian's probably got the best thing that exists now, but hopefully there will be a nationally available resource for that coming out of NCHRP soon. Todd, you asked a question about self-cleaning. That's what we have found, is that these grooves, they don't stay plugged up for long. The only time that we've seen it is, again, due to the geometry of our test section. The shear forces in the surface are intense. And so there's times where it sort of eats the rubber and the rubber gets lodged in there. And there are some instances of that, but I would say, 200 feet, 15 feet wide, there's maybe a dozen of those little, the size of a quarter. So really it insignificant, and show me a road that's got a 15% cross slope that you're gonna have to do this on. But that doesn't really exist. Brian, I think we're going a little over, but I think Andrew Wargo had a really good question. I think we should maybe just end on this. Talk about issues with snow and ice removal on grooving.
Yeah, that's a great question. I was an extra with snow and ice removal when I was at ODOT. So plowed snow, spread salt, brine, all that stuff. And I was an extra, so I got the bad shifts working at night, and I can tell you, uh, it's more of a problem or my experience, I guess, would come more from Portland cement concrete surfaces that were grounder groups, so like a bridge deck or a pavement, right? So I think it's a bigger issue with the light colored pavements. It's really hard to tell when a concrete pavement has ice versus just being wet from like a salt brine when you've got enough material on there that you've turned the ice to liquid. And then there's an issue of, I think it would be really, really great for like these winter maintenance folks or these pool fund studies to know, between your pre-treating materials or your anti bonders versus melting ice once it's formed, right? How to the impact that has, because you're increasing your surface area. So there's a school of thought where if you're pre-treating, that material is you're going to have more of it staying, and the tires aren't going to wear it off because those grooves are holding it, below the contact area of the groove or the tire. So it's really an unknown, I would say. But I think the grooving, you still get the mechanical bite once you have the grooves exposed, even if there's a little snow or moisture in them. So hopefully I've addressed your question there.
And somebody from FDOT, I'm not sure who it is. It's noted they have 4 longitudinal grooving projects on asphalt right now on the books. One is still paving and scheduled to be grooved. That's going to be really interesting, where you've got a very fresh mix and not one that's old. But he talked about transverse grooving and longitudinal grooving. You see a lot of transverse grooving on airports. You don't. Hey, Rich, transverse grooving on airports, because the speeds are a lot higher and you've got to get the water out, and that's the shortest route for the water to get out from under the pavement is to the side. Vehicles are not traveling that fast, and so it's you've got time for them to be able to move that water, to be able to move longitudinally, and you still have the friction necessary that you need. Also, it's the longitudinal grooves are quieter, and they have the mechanical bite. They kind of keep you they're like bumpers in bowling. They keep you moving, even though some drivers don't like that. They're safer, but sometimes people like full control. But anyway, this has been great. Brian, I just want to personally thank you again. Most of what I know about this topic, I know because of you, and I really appreciate you joining us today. It's been great. So, as always, lots of information on our research at the test track, and we love holding these webinars and really getting this information out there. But lots more reading if you're interested. Training in your pocket. So Travis and his team do a wonderful job of making some of the more complex topics easy to understand and approachable, and so and with a little bit of humor in there as well. So this is a great resource, especially for people who are maybe trying to get a little more exposed. Training, we do a lot of training. Travis is great at it, and so we've got lots of industry courses and agency courses available. You guys can come to us, we can come to you. Travis is doing a wonderful job at kind of growing that program, and we love getting an opportunity to assist in training the industry and improving the knowledge base of asphalt pavements. So this concludes our webinar series for 2025. We will not be meeting in December. It's going to be a week before Christmas, and most people's offices will be winding down, or maybe would have already wound down at the time. So we are going to pause, and we're going to pick back up a whole new suite of topics starting in January. Travis and I actually have a date scheduled where him and I are going to sit down and think through, hey, what's the next one's coming through? Maybe we will have some more safety related topics with Florida DOT's got some new OGFC work coming out. Kentucky's got some new work with some of their friction stuff, but also mixture additives and best practices, things like that. So y'all stay tuned, and we will see you at TRB. And if not at TRB, we'll see you January 15th.